and welcome back. Now this is the last session, but I've been looking forward to this session all day because security of ZKP applications it's a really hard problem. As I was saying earlier, it's somewhere where if your money's gone, you may not even know it's gone for a long time. Blockchain security is kind of hard anyway. We're all familiar with all the famous times when it's gone wrong, so I won't repeat those. If we add a ZK layer on top, we've made it even harder for ourselves. So I thought it'd be really good to hear from Dominic and Simon from ChainSecurity, because these guys are real experts in this field. They can tell you what goes wrong and how to put it right. So I'll hand over to them. Okay, thanks Dominic, thanks Simon. Off you go.
Thank you. Thank you. Good afternoon everyone. It's great to see you all here. When applications handle significant amounts of funds or private data, security is crucial. It's essential for users to trust this system, as their confidence is key to widespread adoption. This is particularly true for emerging technologies like zero-knowledge systems, which may be challenging to grasp for those not deeply involved already. Any security breach could deter users and significantly hinder the adoption of this technology. Given that these systems are very new and we are all still exploring and learning about their pros and cons, realistically, we can expect some security challenges with such applications. Today, we're going to dive into the critical role of security and discuss how to secure zero-knowledge applications. Our goal is to prevent security issues, make these applications as safe as possible, and hence enable trust. I'm Dominic Brütsch, one of the lead engineers and co-founders of ChainSecurity. Alongside me is my colleague Simon Perriard, a senior engineer with our firm. We are a Swiss-based company that originates from ETH Zurich, the university. Since 2018, we have specialized in providing blockchain security services, focusing primarily on reviewing decentralized finance applications. Now, without further ado, I'll hand it over to my colleague to lead the first part of our presentation. The screen.
Thank you, Dominic. First, I will quickly go over the agenda. We will quickly talk about what is a ZK app. Then we will go into the challenges that each layer presents. Then we will go over the best practices, and Dominic will also finish the presentation with some takeaways and summaries. So what is a ZK app? A ZK app has two advantages. The first one is privacy. It would allow users to hide their actions or even hide who they are. For example, we can replicate like cash transfer. If I want to give 10 francs to Dominic by signing a transaction on a blockchain or do it by a bank transfer, people can see that I gave him money, right? And I may not want people to see that. But if we use a privacy layer like Nightfall, for example, the cryptographic layers in there would allow us to transfer value without letting the world know how much and who transferred value to whom, right? So in that sense, it would be similar to a simple cash transfer between individuals. Another application is digital identity. Let's say I want to buy a beer somewhere and the cashier asks me for my age. In this case, I could provide a little zero-knowledge proof that I am old enough to get that drink without having to show my ID and thus disclosing like my name, my birthday, or my identity. The second advantage The second advantage is the scalability. The ZK proof systems allow to compress information like complex computation, for example. So if I want to verify a complex computation, I want to know if it was run correctly. What does that mean? Actually, it means that the output that was generated is actually the correct output we should expect, provided some inputs and a computation. But I don't want to run it all again because it's very long, right? So we can run the computation and create a short proof that can be very easily verified. And an example of this would be layer 2 zk-sync era, where we can prove the state transition of that layer 2 blockchain. We can prove that they follow a certain predefined set of rules. And then we will post that proof on Ethereum. And why do we do this? It's basically to inherit the security of Ethereum consensus algorithm. On this slide, you have a quick example of how it works. So on the top, we have some users, and he's doing some transaction on the layer 2. The transactions are included in the blocks, and the blocks are executed. Now the prover of that blockchain will take the block, execute them, most likely following the predefined rules, and a proof of the validity of the execution of that block will be provided. And finally, the system will post that proof on Ethereum. Now let's quickly go over some properties of ZK apps and such proof systems. The first one is called completeness. It basically means that every correct inputs can always yield a valid proof. The second one is soundness. We can define it as basically no invalid inputs can ever produce a valid proof. And the third one is the zero knowledge property, which we may want in case we want privacy, right? Because it means that the proof does not leak any information about some private inputs. So let's go over the architecture of so-called succinct non-interactive argument of knowledge, or SNARK in short. Basically, in the following slides, I want to convince you that those proof systems are really complex and that we need to be careful about each of the critical building blocks. So we start first with some NP relation we want to prove, and we have some public and private input. Very good. We will encode this relation in a circuit, which is a bit like code. We will see some examples later. And now we have the second building block, the application front end, where the circuit will be compiled into some intermediate representations. This is called arithmetization. There are multiple ways to do it. And we also have the witness generation. Witness generation will basically prepare all the inputs for the circuit. Next, we have the application backend. It's composed of a setup procedure, a prover, and a verifier. So the setup procedure will consume the circuit and some common reference string. Why the common reference string? It's to ensure that the setup is deterministic and it can be repeated. So we can always have the same proving and validation key. Next, the prover will do its work and it will generate a proof that most likely will be able to be verified by some verifier. And now the last block is the integration. Here, I took the example of a smart contract because this is what I see most of the time. Basically, the smart contract will consume the proof, it will verify it and validate whatever we wanted to prove. Okay, so I believe I could show you that CK systems are complex and are made of critical blocks, meaning the circuits, which is basically a set of constraints, the front end, the back end, and the integration. Now we will see that we can have some challenges for each and every of those layers. The first one being the circuits. So as you may know, writing circuits are fairly easy, but for a circuit to be correct and efficient, it's actually very hard. Why is it so? It is because the developers need to adapt to a different way of thinking when it comes to circuits. Because when we write code, we basically write instructions, we write what we want the computer to do. And when we write circuits, we write some relations between some input and some outputs. And in the circuit, nothing is computed in the circuit, right? We provide some inputs and some outputs, and the circuit will ensure that the relations hold. We have here a quick example of how to get a square root in a more traditional code and in a circuit. So in the code, we simply ask the machine to compute the square root of b. And in the circuit, the computation of the square root will actually happen outside of the circuit. And we will provide this value to the circuit as an input that will be called a hint. And how do we ensure that a is actually the square root of b? We will simply put a to the power of 2 and check that it is equal to b. Some common challenges we face when we look at circuits are mainly assigned and unconstrained signals that we basically put a signal in the circuit, but we forget to constrain it. We have some other kind of input sanitization problems. We will see later that the proofs work in some finite field, and we can have some funny things in there. We can have some external hints that are not constrained enough. Sometimes we reuse libraries, but we reuse them wrong. This can lead to some problems, or some languages that have some keywords that looks actually nice, but that aren't safe. Now some examples. For the finite fields, on the left, you can see that we have some circuits, and we want to ensure that the sum of the user's balance is equal to some total supply. So we have our balances as the total and the total supply as inputs. And in the circuit, we will sum the balances in this intermediate variable called sum. And we will check that this sum is equal to the expected total supply. You can actually ignore the value d here. It's just for the compilation to succeed. So in our example, we will have a total supply of 100 tokens, and we will have 5 holders. Now the first holders have 20, the second one also has 20, third one same, so far so good. Then the fourth one has 100, which seems a bit weird because it's the maximum number of tokens we should have. And the fifth one has a huge number. So what happened there? So as I previously mentioned, we are here in a finite field. So in this finite field, if we sum up those 5 values, we end up at 100. So we need to be very careful and check that some of those values in the circuit are not bigger than a certain number to avoid some overflow problems. What do we do to fix this? As the comment says here, we need to do some range check at some point. Second example is about unconstrained external hints. And here on the left, we want our circuit. We want the output C to return either 1 if X is equal to 0 or 0 otherwise. We have this signal inf, which is actually a hint, and it's computed during witness generation and somehow fed to the circuit as input. And maybe we can say, okay, we trust the witness generation and we will blindly use the value. Well, if we actually trust the value, we can end up with some problems. As we can see on the right, if the witness generator can be manipulated or is actually buggy. On the right, our input X is 5, and the actual output we should expect here is 0, right? Because 5 is not equal to 0, so the circuit should return 0. But if we manage somehow to set the inf to 10, for example, which is not the inverse of 5 in the field, then our output C is extremely wrong and does not adhere to 0 or 1, right? So the fix here is actually one more line. We need to add that constraint to ensure that either X or C is 0. And this will guarantee that the output C will be either 0 or 1 and no other weird value. And the last example, we want to ensure here that the hash of the concatenated values A and B is equal to C. And we also want to we want this constraint to not hold in the special case where C is equal to 0. And we have this very nice assert keyword in the CIRCOM language, and it seems to simplify our life quite a bit because we don't have to write some complex constraints. But as you may know, there is no free lunch, and this keyword actually does not add any constraint in the circuit itself. It adds some checks in the witness generation, but if we use this keyword in the circuit, it's like it doesn't exist from the perspective of the proof. So it means that we can actually provide any value for A, B, and C. There. So if we put an assert, the circuit is exactly equal to the one without the assert, and we can provide any value we want. Now we will quickly go over the remaining challenges. So for the front end, it could happen that some wrong optimization gets rid of some critical constraints. On the side of the witness generation, if it's buggy, it may be possible to, for example, DOS the service, which could be quite bad. Let's talk about the backend challenges. We can have some adversarial provers that may leak private inputs, for example, or also manipulate the proof if circuits allows it. We may have some issues during the common reference string generation if some example toxic wastes are not properly deleted. This would allow some attacker to forge proofs that would verify, but that actually are wrong. And we can have some other more classical bugs in the prover or in the verifier. Regarding the integration, some circuits would expect, let's say, the smart contract that verifies the proof to check for some inputs. So it would unload the input sanitization to the smart contract, but the smart contract may not implement those checks. So we may run into some problems there. Sometimes the proof can be misused. For example, we run the verification, but we don't stop the execution if the proof fails. That kind of problems. And for proof systems that do proof aggregation, it can happen that the proofs are put together in a wrong way. And finally, we will quickly go over some cool bugs that happen in the in the space. The first one is called Frozen Heart. It's about an insecure Fiat-Shamir transformation where the protocol does not hash the full transcript, and it can lead to forgery of proofs and thus loss of funds. The second one is some missing point on curve check, where the library was doing some operations on elliptic curves, and the final points were not checked to be on the curve. And this would also allow some attacker to forge proofs. And the last one is minting infinite money on Nightfall v3, where some missing constraints in the circuit enable the creation of infinite money and thus training the system. I will now let Dominic talk about the best practices.
Thank you, Simon. Those were some impressive examples of what could go wrong. Such demonstrations are great to raise awareness. The more aware the project lead and the development teams are, the better. This helps the whole team to understand the importance of taking security seriously. This next section is focused on how to securely develop such an application. After 6 years in the industry, mostly reviewing decentralized finance projects implemented as smart contracts, we've seen a lot. A lot of blockchain smart contract experience translate well into the development of ZK applications, albeit there are some differences. Security begins way before the launch of your ZK application, even way before the development starts. Before your team begins coding, it's important to have a clear understanding of what you intend to develop. Outline your implementation by detailing what it provides, the problem it solves, and how it addresses that problem. Do you plan to add certain functionalities at a later stage? Only once you have a thorough understanding, you can design the application and make an informed decision about the software stack to use. This space is rapidly evolving. There are many frameworks out there that you can use. There's no single go-to framework, each has its trade-offs. Different frameworks offer various strengths and drawbacks, such as proof of verification time or size, or ease of implementation and extension. Your choice will depend on the specific needs of your project. Additionally, the security of the framework is crucial, as any vulnerability impacts your project. A new cutting-edge framework may have all the benefits you would like to have, but would you use it or rather go with a more battle-tested solution? We know it's tempting to start developing as soon as you have an idea, but this often leads to significant technical debt that becomes difficult to resolve later on. If time allows, consider implementing a minimum viable product to test your concept or refine your solution. However, avoid the temptation to build the final product directly on top of the MVP, as this usually causes problems. Over the past years, we've seen numerous projects suffer from fundamental issues that are extremely costly to fix late in the development cycle. Money may have already been spent on development and possibly even external reviews. Most of this investment can be lost, plus the launch must be delayed until the core problems are addressed. One crucial point, particularly for non-technical decision makers, is that simply assigning software engineers to develop ZK applications can be tricky. Although many frameworks support Rust, a language your developers may already be familiar with, the execution model and the mindset required to understand ZK application are vastly different from traditional software engineering. There's an ongoing debate in the field about the depth of understanding developers need regarding these mathematics to develop secure application on top of that. A sound understanding of the underlying math is certainly beneficial, but expecting all developers to have this knowledge isn't realistic. Since the framework often abstracts most of the math, the good news is developers don't necessarily need to grasp all the mathematical details. However, they must be at least familiar with the core concept. And yes, misunderstanding can lead to severe bugs, for example, if the abstraction isn't as expected. Now, if you plan to implement a ZK application, usually you won't need to reinvent and redevelop the entire stack. As my colleague Simon explained earlier, zero-knowledge technology enables two key features. On one hand, the privacy-preserving ZK port, which allows you to perform computation without revealing some inputs. And on the other hand, as a consequence of the technology, it provides a succinct proof of correct execution. Some of the most well-known Projects in this field implement virtual machines in ZK technology to prove the output of a computation. These make use of the succinct proof property, not the zero-knowledge aspect. For such complex projects with highly specific requirements, you need to build everything yourself. For the vast majority of ZK applications, however, especially those focused on the zero-knowledge part, such an extensive development is unnecessary, and the expenditure would not be justified by the scope of the application. Here we focus on these smaller, more tangible projects. In practice, you implement the circuit that represents your application logic. While there will be additional software and front-end components, the circuit is truly the heart of the application, particularly from a security perspective. It implements the core ZK application where the restrictions of the protocol are enforced. Of course, if there are implementation bugs in the prover or verifier, or if the scepter procedure has been done incorrectly, in this slide this is shown in the backend part, these issues can also be problematic. So what options are available? We've mentioned frameworks earlier, but it's important to clarify that it's not just about different frameworks implementing the same concept. In simplified terms, there are multiple zero-knowledge protocols or technologies. Let's focus on SNARKs, succinct non-interactive arguments of knowledge, and STARKs, scalable transparent arguments of knowledge. SNARKs can be implemented in various systems, such as Modeling or Blanc, which typically originate from research papers. For the actual implementation, you'll need a library and a framework. We've listed some on this slide. Great. Let's get back to our project development. We've outlined our project, selected an appropriate framework, and began developing. What's important at this phase? This part isn't much different from traditional software development. It's crucial to have good procedures in place, conduct internal code reviews, implement proper testing, and maintain thorough documentation. Generally, tooling can help. However, in this nascent field with many different frameworks, good tooling is rare, unfortunately. For any critical software, particularly the core implementation of a ZK application nearing production launch, an independent external review is crucial. Such a review, conducted by experts with extensive experience and domain-specific knowledge, brings a fresh perspective that can identify potential pitfalls and provide valuable feedback. Moreover, this external review helps ensure that the implementation aligns with the documentation and specifications. The resulting report can also serve as a demonstration of due diligence to stakeholders. Choosing a competent and trusted partner for this task is essential. It's important to select a company that is well suited for this type of review by examining their previous work and seeking references. This external party should develop a comprehensive understanding of your system and conduct a thorough examination. They are tasked with identifying any overlooked issues to prevent them from making their way into production code where they could be exploited post-launch. However, it's important not to view an external review as a magic solution that can resolve all issues no matter what the state the project is in. While such reviews are excellent for uncovering unexpected problems or security vulnerabilities, addressing major foundational issues at this stage is very difficult. Security doesn't end once your application is launched. This is crucial. Typically, you would implement monitoring to ensure the system behaves as expected, but this can be particularly challenging for ZK applications that across details of user actions. Detecting errors in such environments may be difficult. It's also essential to run a responsible disclosure program. This is considered industry standard, with major companies like Microsoft, Google, and Apple setting an example by offering programs that allow anyone to safely report problems or vulnerabilities without fear of repercussions. Establishing such a process is vital, as it enables good actors to report issues and receive rewards rather than leaving vulnerabilities unreported and potentially exploited by malicious actors. Furthermore, while every project leader hopes that they will never face a security incident, having an incident response plan in place is critical. This plan should define who is responsible, how and when they are reachable, and who will be involved in managing the situation. In the event of a security issue, it's important to control the flow of information until the problem is resolved. For such situation, you should have a plan in advance. Lastly, don't overlook the need to monitor your dependencies, such as the framework you use. Be vigilant whether issues are detecting these components, as they can affect your project. This brings us to the end of our presentation. We hope we've been able to illustrate some of the challenges involved and highlight the importance of sound development practices for your ZK application. If you have any question about this presentation, ZK security, or blockchain security in general, please do not hesitate to reach out to us. If you're working on an actual project, it's best to consider all of these aspects early on. We'd love to hear about your project and discuss security with you. Don't hesitate to get in touch. Thank you for listening in.
Dominic and Simon, thank you so much for that. That was every bit as fascinating as I thought it would be. And I was sitting here and I completely forgot I was in a TV studio listening to that. Marvellous.
Thank you.
So many takeaways, one of which is never forget you're working in a finite field. And the other is be really careful about your DSL that you're using and its little quirks. So brilliant. Thank you so much. We do have a question or two, actually. So the first one, I'm not sure quite what that refers to. Why was the choice of setup deterministic? Any clues? No, I think we'll leave that one. It's kind of out of context, so not to worry. And the second one is, oh, that's an interesting one. So somebody is asking, are there any tools available that might help you with your ZK security, or is everything too early for that?
There are some static analyzers and even some companies developing formal verification frameworks. So formal verification is kind of the gold framework, gold standard, right? Because you have something and you can prove that it behaves correctly. But whether this works for your DSL or for your system, best to Google static analyzer or formal verification for the DSL you have in mind.
Yeah, okay, great. Well, that's all the questions. Gentlemen, thank you very much for your time. I much appreciate it. And that closes the last session. Right, which also brings us to the end of this year's ZK Summit ZK Summit. I've got ZK on the brain. Blockchain Summit, of which we've now had 8, I believe. I've been around for 7 of them, so I'm doing quite well. Haven't been fired yet. It's been fascinating as always. I love the mixture of sort of technology and business applications, and thinking about regulation and things that matter. So I hope you found it as interesting as I did, and we'll be back next year with more. I'm not sure from where. We've been in London the last couple of times, but maybe we'll move somewhere else. So we're open to invites. Okay, bye for now, everyone. Thank you very much.